Today's lesson focuses on an area of chemistry called stoichiometry. It is the chemistry behind chemical reactions and us predicting the amounts of substances within that chemical reaction. Stoichiometry involves balanced chemical reactions. And when we use stoichiometry, we're also using something called a mole ratio. So what is the difference between the two? Well, stoichiometry is this branch of chemistry that is making predictions about substances or the amounts of substances in a reaction. And mole ratios are what we use in order to create or make these predictions. And they come from our balanced chemical equations or our reactions. And we will still use our mole concept. We're just going to be putting it together into a chemical reaction where we have more than one different substance. So what is a mole ratio? Well, a mole ratio is a mathematical expression. It is an actual ratio that we're going to be setting up. And a mole ratio can only work for two substances. So even though we're going to be looking at chemical reactions now that likely have more than two substances in the reaction, you can only use the ratio for any two substances at one time. So the mole ratio has the following features. First one right here, it is derived from the balanced chemical equation. So you have to have a balanced reaction every single time you undertake stoichiometry. And the coefficients in our reaction are extremely important. There should be an arrow there. So we know how to balance an equation. We understand why we do that based on the law of conservation of mass. But now what do these coefficients mean? Well, previously you probably would have read a reaction like we have here by saying one molecule of methane would react with two molecules of oxygen to create one molecule of CO2 and two molecules of H2O. But what we know now based on the size of atoms and molecules is that we need so many of them to accumulate in order for us to see them or get a sample of them or react them. So instead of talking about atoms or molecules, we're going to refer to these substances as moles. And so we read this as 1 mole of methane, which is 6.02 times 10 to the 23, is going to react with 2 moles of oxygen, which is just 2 times 6.02 times 10 to the 23. It's going to produce 1 mole of CO2, and it's also going to produce 2 moles of water. So we like to use the word mole better than atoms and molecules, and we understand that we can. There's a relationship with Avogadro's number to allow us to do that. And that is what our mole ratio will be representing, is the mole values of our substances. The reason we use them, though, is because when we carry out a reaction, so for example, let's conduct a combustion of methane, we may not have 1 mole. So what if you have 2 moles? What if you have 3 moles? Well, the proportions stay the same. Okay, so the proportions are the same, and then you can just scale up or scale down the mole ratio from the balanced equation. So if I was going to react 2 moles of methane, which is a factor of 2, I would apply that factor to everything in the reaction. When we use whole numbers, it's not so hard to come up with a mole ratio and figure out or predict amounts of substances. But when we use decimal places or we have a strange coefficient setup that's a little bit harder for us to do in our head, we need a systematic way of setting up a mole ratio. And that's what's happening here, is that we'll set it up in a way where we have numerators and denominators, and we put unknowns on one side of the ratio, and we put our givens or our knowns on the other side. So let's go through an example of a mole ratio. This is an easy one because we're using whole numbers and we're using a reaction that is relatively easy for us to set up. It says, predict the amount of hydrogen that will react with 6 moles of oxygen gas to produce water. So the very first thing you must do is set up your balanced equation. We now understand that these coefficients are very important, and they're going to allow us to predict amounts of each of our reactants in our products. So it says that we're going to take hydrogen and react it with oxygen gas, and we're going to produce water. So we'll set up our reaction, and we have to balance this. So let's balance our oxygens by putting a 2 in front of water and put a 2 in front of hydrogen. So again, when we read this reaction, we are saying 2 moles of hydrogen will react with 1 mole of oxygen to produce 2 moles of water. But we're not starting with 1 mole of oxygen right here. We're starting with 6. So what we like to do is always write what we know beneath the substance. Okay, so again, I'm not starting with 1 mole, I'm starting with 6. However, the proportions are the same. To go from oxygen to hydrogen, it's a 1-to-2 ratio. And so this is very easy for us to do just in our mind. We can say I need twice the amount of hydrogen compared to oxygen. So the moles of H2 that I need is going to be 2 moles of hydrogen for every 6 moles, multiply, of oxygen. And we get an amount of 12 moles of hydrogen being needed. So again, this one's not so hard. We have whole numbers, we have easy ratios. We can kind of do that in our head and understand the difference. When we're given decimal values or ratios that are not so easy to use, like a 1-to-2, we need a systematic way of setting up our mole ratio. So let's look at this example. It says calculate the moles of ammonia produced when 2.3 moles of hydrogen reacts with nitrogen. So let's set up our set up our reaction first. So we're going to take hydrogen gas. We're going to react that with nitrogen, which is a diatomic. Again, nomenclature extremely important. And then we're going to make ammonia, and ammonia's formula is NH3, which is also a gas. Let's balance this. So my hydrogens are not equal. We're going to multiply each hydrogen value by the opposite coefficient. And then my nitrogens become equal as a result of that. So when we look at this, we are going to create 2 moles of ammonia if 3 moles of hydrogen and 1 mole of nitrogen react. Well, we're not starting with 3 moles of hydrogen. The question is telling us that the moles of hydrogen that I'm starting with is 2.3. And they're asking us what is the new mole amount of ammonia. So this is a little bit harder for us to do in our mind. We're using decimals. We're using a 3-to-2 ratio. So what we'll do instead is we'll set up this ratio. And what we do when we set it up, we put our moles of our unknown substance in the numerator of 1/2 of the ratio. And we compare that to the moles of the substance we have been given. So we've been told we're going to use 2.3 moles of hydrogen. How many moles of ammonia is going to result? And then we equate this to what we call a fixed mole ratio. This is the ratio out of the balanced equation. And you must set it up so that you have the constant for ammonia written on the same side as the constant for hydrogen. Okay, so if my ammonia value is unknown and I put in the numerator, then I need it in the numerator on the other side. So again, this is what we call a fixed mole ratio. And it's fixed because it's based on the coefficients in the reaction. They're the same all the time. They're fixed. This other side here is my unknowns, okay, or my givens in the question, okay, or my actual values. You can call it anything you want, but these are the values that change. So we're going to just simply cross multiply. We're going to take 2.3, we're going to cross multiply it by 2, divide by 3, and my moles of ammonia works out to be 1.53 mole. Rounded to 2 sig figs, I need to have, get my pen, 1.5 moles. Here's a last example that we'll do, setting up a mole ratio. So it says calculate the moles of oxygen needed to combust 0.75 moles of ethane. So let's set up our reaction. So we always assume complete combustion unless they tell us otherwise. So ethane would be a gas. We're going to react that with some oxygen gas. And if it's complete combustion, we're going to create CO2 gas. And we create water in the liquid form, which quickly evaporates. We need to balance this. So in order to balance this, we're going to have to even up my oxygens initially. So I need a 2 out front of ethane, which causes me to put a 4 there, a 6 in front of water, and then I've got 14 oxygens. I need to put a coefficient of 7 there. So it's saying calculate the moles of oxygen needed. So this is what I do not know, to combust 0.75 moles of ethane. So I know how many moles of oxygen I need if I was going to combust 2 moles of ethane. I would need 7. But I don't have 2 moles of ethane being combusted. I have 0.75 moles. And so we can quickly set this up and calculate the moles of oxygen that we need. So remember, we put our unknown amount in the numerator. We compare that to the amount given to us in the question. So 0.75 moles of ethane. And you have to write in the formulas of everything. I mean, there's 4 different substances here. You need to organize your work so that we know exactly where these values are coming from. We know that this ratio is 2 to 7. The proportion is always the same, so we're going to apply that. So remember, you set it up with the coefficients now on the other side related to what is in the numerator of your ratio. So we're trying to figure out the moles of oxygen. We know we would need 7 moles of oxygen if I was going to combust 2 moles of ethane. Again, just setting this up and solving for the unknown. So we're going to take our denominator down here. We're going to cross multiply it by 7, divide it by 2, and I'll just set this up for you over here, okay, just in case anybody needs help with that. So we're going to take that denominator, so 0.75 moles of C2H6, and we're going to cross multiply it by 7 moles of O2, and then divide by 2 moles of C2H6. This allows my moles of C2H6 to divide out, cancel out. And when I do this math, I end up with 2.63 moles of oxygen, and rounded to sig figs, I should have 2.6 moles.